Okay, hello everyone, my name is Bouke. My talk is called Hacking Go's Internals. And first I'm going to explain what I mean by hacking Go's internals. So whenever I use a tool, be it a library, a package, or a programming language, I like to not just use the tool, but I like to actually deeply understand it. So if I use a programming language like Ruby or Go, I don't just read the documentation and start programming. I usually also like to actually read the source code of the programming language and try to understand what goes on behind the scenes and get an understanding of what the thought process was of the creators. So what I'd like to do is I'd like to transfer some of that knowledge because I think that having this deep knowledge allows me to be a better programmer. So I hope you can learn something. And what I'm also going to do is I'm going to show how if you know some of these inside things, you can hack them and do fun things. So what I'm going to explain is, first I'm going to show you what happens before a Go program can actually run. I'm going to explain a bit how deferring and panicking works behind the scenes. I'm going to show you a trick that Go uses that allows it to have thousands or tens of thousands of thread of execution without using a lot of memory. I'm going to show you how I can run private functions that I'm not supposed to be able to. And then I've got a surprise at the end that I got feedback like this from. People would call me evil for it, so it's going to be a fun one. So first I want to talk about what kind of programming language is Go. And I basically created three arbitrary groups and tried to place it in it. So on the left we have interpreted or scripting languages like Ruby and Python and JavaScript. In the middle we have classical compiled languages like C and C++ and newer ones like Rust. And on the right we have JVM languages like Java or Scala or Clojure. So what's special about JVM languages is that they retain a lot of type information at runtime, so you can inspect objects and get information from them. So at first look, you would think Go is a compiled language because you compile it and you end up with a binary and that's what you run. But what's interesting is that Go actually shares a lot with the other columns because Go has a garbage collector. It doesn't do the same thing as the other compiled languages where you can just allocate memory and it takes care of it for you. And what's also special about Go is that it actually has reflection. So you can, at runtime, you can see what methods and what values are defined on an object. And you can run them and you can iterate over them. And this is also a reason why Go has very large binaries, because it needs to keep a lot of information in the binary, but this gives it the advantage that you can obtain a lot of information about the code at runtime. So let's look at the very simplest possible Go program. This is a program that in the package main, and the function is called main, which is a Go convention for the entry point of the program. So all this program does is it prints the number 1 and then it's done. And before that function can actually get run, there's a bunch of things that need to happen in order to be able to run it. So I'm going to start from the top, which is the entry point of Go. And it starts with a function called rt0. So what rt0 does is it just gets the arguments that are passed in the command line and saves them for later. Then it starts main. All main does is it goes to a function called runtime rt0go. So rt0go, its purpose is to set up the scheduler and the first Go routine and the runtime, because at this point, it's not really a Go program yet. There's no Go routines, there's no garbage collector, there's nothing. So what it needs to do is it needs to set up the scheduler, it needs to set up the first Go routine, which means allocating some special structures that hold all this information, setting up a bunch of things, and then it kicks off this first Go routine. So this first Go routine, what it does is it runs runtime main. Runtime main, at this point, it's an actual Go routine, so it's pretty close to what we need. But there's still a bunch of things that need to be set up. So it calls runtime init, which set up some global variables it needs, and then it calls main init. And main init is kind of a special function, and if you've used Go, you know about probably know about the init functions. So what an init function does is it allows you to specify some functions that you need to get run at startup. So this is handy if you need to set up some special variables. And main init is actually a special function because it also makes sure that all the dependencies get initialized. And when it's done, then the actual main function gets run, and When that's done, runtime main just makes sure that the program exits. So now that we have a bit of an idea of how running a Go program looks, I'm going to explain how one of Go's main features work, and that is deferring and panicking. So what deferring allows you to do is it allows you to say, I want this function to be run before this function completes. So in this example, I say I want to defer D, and then when main is done, it runs D, and it guarantees that this function gets run no matter what. So here, I panic, which is a way to shut down the whole Go program to say that there's an error. But because I defer D, Go makes sure that it says hey before it panics and quits the program. So at this point, I wanted to look through the Go source code and find out how does this panic function work. So I went to the Go source code, grabbed for panic, but there's not actually a function called panic. And at this point, I used a tool called Hopper. And what Hopper does is it's a disassembler that has a lot of nice features. So it makes it slightly readable, even though it's still assembly code and it's hard to understand. So here's the disassembly for the main function I just showed you. And as you can see here, there's a call to a function called runtime go panic. And if I look for go panic, I find the actual function. And the reason it's called go panic and not panic is because Go's runtime is actually written in Go. And because panic is a special function, they couldn't call it panic, so they need to call it go panic. Okay, so when I look at panic, it does roughly three things. It doesn't immediately crash the whole program. What it first does is it goes through all the defers from bottom to top. So it looks at the last one and then goes through them until there's no left. And actually a thing in Go is what you can do is you can recover from a panic, but I'm not going to get into that. And if you're interested, you can look through the source code yourself. So when it's done going up through all these defers, it'll stop everything, print stack traces for all the running Go routines, and then kill the program. And something you'll notice if you look through the Go runtime source code is that there's a lot of references to this function getG. And what getG does is it gets you a reference to this internal Go routine structure. So at the beginning when I mentioned about the start of the Go program, is that Go creates a special Go routine function or structure that it stores everything about the Go routine in. And it's huge. It contains everything about the Go routine. It contains where the stack is, it contains information about where it was started, what the thing was that it started with. It contains information about garbage collecting, everything. And it also contains panics and defers. So when your Go routine starts panicking, it saves the panic in the Go routine. And it needs to save it because there can actually be multiple panics at the same time. So if you panic in your defer, you crash multiple times at the same time. So panic is, it's a list. So it can refer to another panic. So you can have like a linked list of panics. And defer the same way because you can have multiple defers. So when you create a defer, it saves it in here. And if there's another defer, then it links to that. So you can have a list of defers that are linked. Okay, so now that we know where defers are saved, let's look at how the actual defer function works. So once again, I use Hopper to see what this code creates. So on the left, we see defer D. And if we look at the disassembly for main, we see a call to a thing called defer proc. And if we look at defer proc, we once again see that it references getG. And basically all defer proc takes is it takes a function, it takes the arguments, and then just saves them in there. But once again, it uses getG. So at this point, I was like, okay, this is cool. Like, I think I kind of understand it, but I want to be able to actually mess with it. I want to be able to get the defers and get the panics and do stuff with it. So I wanted to be able to call getG, but because getG is actually a special function, a special because it's only available in the runtime, and it's not an actual function because what the Go compiler does is if it sees getG, it inserts some magic numbers to be able to get a reference to this Go routine thing. So I looked through the Go documentation to see like how can I do this myself. I found some references in the Go assembly guide. So in Go, you have your nice garden of Go with your type safety, but you can also write assembly code if you need to make stuff go faster. So I basically just copied and pasted some code together to write my own getG function. And as you can see, I return a Go routine there. And because Go is written in Go, I can just copy and paste the structure that Go gives you for Go routines. And I can make everything public so I can actually access all the variables. And now I can actually use it. So here I have an example where I create a program that defers some things, and then I can list all the defers. I can go through them and print the names. And this is normally something that's entirely a bad idea and you shouldn't do this. But now it's possible. So I defer to functions, then I use getG to get a reference to the Go routine, and then I can go through all the defers, find out what the name of the function is that's being called, and I can print them out, and this is the result. And you can do way more malicious stuff with this, because now that we have access to this, we can actually change things. So here I defer to two functions, I get the Go routine, and what I do is I remove one of the defers. I overwrite it with the next defer. So here I have two print statements. I get called, but I don't. And after I say, well, who will get called, normally it would call the second one first, because that's the last one. But because I remove it, it never gets called. So normally defer is used for like cleaning up things. For example, if you open a file and you want to make sure it gets closed, you would use a defer. But you can use this to create all kinds of havoc in your program, if that's what you want to do, of course. Okay. Now that we know how defers and panics work, I'd like to explain another one of Go's big features, which makes it possible to have thousands or tens of thousands of Go routines without using a whole lot of memory. So in other programming languages, if you create a thread, what will actually happen is that the operating system will give you a bunch of memory to use for this thread, and you can't really grow that. You just get a bunch of memory, and you can run a command to find out how much that is. So on my machine, it happens to be 8 megabytes, which means that every time I create a thread on my computer in Ruby or Java or whatever, the operating system gives you this memory, and that's it. And this is also where the infamous Stack Overflow error comes from, because if you use more than that memory, your program crashes. Go does something different, however, because they wanted to have thousands of Go routines, they can't just have 8 megabytes for every single Go routine, because that would balloon the memory and it wouldn't work. So in Go, you actually start with a very small amount of space for the stack. So in this example, I only have 4 values. I have a number, I have a reference to a value in the heap, so that's dynamic memory, that's outside the stack. I have another value, and I have that pointer should be pointing to the one previous, so I can have a reference to something in the stack. And at the bottom, I have some unused memory with what's called a stack guard. So the stack guard is something that Go has to make sure that you don't go through this limit. So when it detects that you're going to use more than you currently have available, it's going to allocate more memory for you. So if you go through a Go program, you will find, within this assembly, you will find that almost every function has the same code around it. And that's here, that's at the top and at the bottom. So what this does is it checks whether you're almost going to use more memory than is available. And when you're going to do that, then it's going to jump to the end and call something called more stack. So more stack just gives you more memory, and then it goes back again, checks if there's enough, does it again. Yes, question?
Can you limit that by the growth of memory that you consume with the Go routine?
Okay, so the question is if you can limit the amount of growth, and the answer is there's a built-in hard-coded limit of, I want to say, 100 megabytes or a gigabyte, one of those two. But you can't really change that, that's just hard-coded. Yeah, so if you wanted to limit the size of your Go routines and the size of your process, you would need to use just one of the built-in Linux tools, probably. You have a question? Or? Okay, scratching your head. Great. Okay, so so this is our state. We just went through the limit, or we're detecting that we're going to go through the limit, and we now need to allocate more memory. So Go will just copy and paste basically your stack and give it double the amount of space so that you have plenty of room. But now there's a problem. Because we have a reference to the stack, this is possible, our new version now points to the old version. And because we want to throw away the old version, we would end up with a problem because we would now be referencing memory that doesn't exist anymore and your program would blow up. Now, this is where it comes in handy that Go has a lot of information about the program while it's running, because it can actually detect, oh, this value is a pointer and I need to change this. So it uses something called the pointer rewriter, and it can just change it to point to the new value. And then we can throw away the old value and happily keep running. Okay, so while doing my research, I was seeing all these cool runtime functions like more stack and other things. And I was like, why do the Go developers get to have all the fun? Like, I want them to call these functions and play around with them. So essentially, I wanted to be able to call any private random function. And while looking for cool functions, I found stop the world. And stop the world is something in the runtime package that basically allows you to say, okay, at this point, I only want my Go routine to run and everything else to stop. So if this is our situation, and the Go routine in the middle says stop the world, then all the other Go routines get paused and until it says start, and everything runs again and it keeps running. So this is used, for example, for printing stack traces. So if you want to print the state of all the Go routines, you want to make sure that they're not running. So you say, everyone pause, I'm going to print it, and then everyone can start running again. So to be able to call this function, we need to be able to find out where it's actually residing in the program. So once again, I used Hopper, and because Go retains all this extra information, I could just type in the name and find out the location in the binary, and it's highlighted there at the top. It's a hexadecimal number. But every time you compile your program, everything gets shuffled around, and this location will change. So we need a way to read this value at runtime. To do that, I created a package called sym.me, which gives you the symbol table for the current program. So the symbol table is basically this big list of this function is here and this value is here. And now we can actually read this symbol table and find out where this function is. So here what I'm doing is I'm calling lookup function. So lookup function, you give it a name and it gives you back the location. And then I say I want the value, so the value is the actual number location. Then I can print it out and I get the exact same number that I got before in Hopper. And to use this, I created some helper functions. So I created a function called insert function. And what insert function does is you give it a name and you give it a function value where you want to store this function. So now you can say, I want to have stop the world saved here, and then you can just call that function. So here's an actual test that I wrote to make sure that this works. So what this does is at the top, it sets a value to true. And then what it's going to try to do is it's going to try to run a Go routine that's going to overwrite this value. And then it's going to check whether the value is still true. So normally in Go, so it does 100 million iterations. So normally this would cause the Go scheduler to see, oh, like this has been running for a while, I'm going to pause it and run this other thing to make sure it's evenly scheduled. But because I say, stop the world, like nothing else gets to run, this just works. It never gets overwritten. And then at the end, when I say start the world, only then does my Go routine get run. So this is not actually useful, but it's interesting that we now know that we can call these hidden functions. Okay, for my last demonstration, I would like to show you one thing that's it's kind of common in dynamic languages like JavaScript and Ruby and Python, and it's something called monkey patching. So if you're not aware of monkey patching, what it allows you to do is you can basically override any function at runtime. So for example, in Ruby, you can actually override standard functions. So here what I'm doing is I'm overriding the toString method for any number. So now if I'm going to print any number, it's just going to say 42, no matter what the number is. So you might be thinking, that's an awful idea, why would you do that? And I completely agree with you, but that's not the point. Okay, so basically what I want to have working is, I want to be able to say, print the result of A, but have it print print the result of A, but instead have it print the result of B. So I'm going to say replace the function A with function B, and then when I call function A, instead I just call function B. And in practical terms, it means that I need to find the location of both functions. I need to actually go to the actual machine code body of the first function and overwrite it with a jump to the other function. So in graphical terms, if these are our two functions in memory with the code body, it's all machine code and assembly, then what I want to do is I want to take function A and overwrite the beginning with a jump to function B, so that when you call function A, it just immediately goes to function B and runs that instead. Once again, this is not very practical, but you know. Okay, so first we need to find out how do function values work. And if you've ever used C or C++ with function values, in those languages, a function value is basically a direct pointer to the location where the function is. But in Go, this is, it needs some more information. So in Go, a function value is actually a special value that references the function. And we can find that here. We set f to A, but it doesn't set f to the location of A directly, but instead to something called AF. And the reason is because function values in Go can have extra information. For example, you can have a instance method as a function value, which means that the function value needs to contain the instance, but you know, just trust me that this is how it works. Okay, so this is the full code of our replace method, and I'm gonna try to go through it line by line and explain. And if I'm going too fast, then please let me know. Okay, so first we need to find the location of the code that we need to overwrite. And normally in Go, you can't just convert any value to any other value, and there's very good reasons to not do that. But it has a kind of trapdoor, so you can subvert all this type safety. It's a standard package called unsafe. So with unsafe, you can basically transform any value into any other value. So here what I'm doing is target is the function value of the function that I want to replace. So what I'm doing is I'm converting this function value to a pointer because we have two layers in direction. And then when I read that, I get the location of the function. Everyone get that? Okay, good. So what I gotta do now is I gotta take this location and then create some assembly code that jumps to this location. So for that, I wrote the assemble jump function. And because we need to reference the function value and not the actual function when we want to jump to it, we only need to do one layer of indirection. And then I'm going to take that address of the function value and put this in this bunch of assembly code. And I wish I could explain why these are the numbers that work. They're by definition magic numbers. They're machine code, so like the CPU knows what to do when it reads this. If you want to know exactly why these numbers work, I invite you to read the Intel x86 manual, which is a 4,000 page book that explains why this is, but just trust me that this is how it works. Okay, so now we have a slice, or in other language, an array of all the assembly code that we need to write. And in Go, if you want to copy an array to somewhere else, use the copy function at the end there. So it takes a target and it takes a replacement. So now we have the replacement, and now we just need the target. And to be able to write to random memory, I created a helper called DMA. DMA means direct memory access. So essentially, you can get a window or a slice of any part of the memory, and then you just copy to that. So here I'm slicing from the beginning of the function up to the amount of bytes that I need to write. So now I have both slices, and I can just use the regular Go function to copy. And now you might be thinking, like, really? Like, just 4 lines of code and you can just overwrite whatever you want? But no, this doesn't work at all, of course, because there's very good reasons to not be able to just overwrite random parts of your code. That's very dangerous. There's lots of security considerations why this is not something that you should be able to do. However, if you ask nicely, you can still do it. So there's a standard function in Unix, so like on Mac OS X or on Linux. There's a different equivalent in Windows, but it's called mprotect. So mprotect, you basically say, operating system, like this part of memory, like you can trust me, I'll just overwrite it and you can execute it later and like there's no problem. So what I'm saying is this part of memory, I want to be able to read to it and write to it and execute it. And normally you can't write to it. So when I do this, it just works and I can just override this memory and when I call the function, it prints the number 2 instead of the number 1. So that's great success. And I wrote a blog post about this and I got some great reactions. Like I'm basically the devil and helping people, and you know, people will yell at you, please don't do this is unsafe. Anyone's gonna do this is gonna go straight to hell. I kind of agree with that, so don't do this. Please never use this in actual code.
You got any bombs delivered to your house?
Sorry?
You got any bombs delivered?
I did not get any bombs delivered to my house. So I know like this doesn't actually work. I actually got a reaction from one of the Go authors that if you do this, then on the next garbage collection run, it's going to crash the whole program because it gets confused. I haven't been able to find out how it actually works. But yeah, like if you do this and you call the function and you garbage collect, your whole program crashes. So don't do this. Or disable the garbage collector, one of those two. So yeah, you can find the libraries that I created for this presentation here. It's github.com/bouke/unsafer. So that's a joke because there's the unsafe package and mine allows you to do even unsafer things. And there's the monkey project that allows you to do monkey patching. Okay, so that's basically it. If there's one thing that I want to have you realize from this is that like most safety in most languages and most systems are kind of fake. Like there's always a way to subvert them. Like computers are just dumb machines and you can always tell them what to do. So keep that in mind while you're working in a nice, safe environment. And thank you. You can find me on Twitter and this is my website. Thanks a lot.
Thank you.